Good day. So let's have our next lesson, unary matrix operation. So the objectives of this lesson are you should be able to know what unary operation are, find the transpose of the square matrix and its relation to symmetric matrices, find the trace of the matrix, and find the determinant of a matrix by using the cofactor method or the cofactor expansion. So first is, what is the transpose of matrix? So let's say matrix A is a M by N matrix. Then B is the transpose of A. If if Bij is equals to Aij for all I and J. So that is the ith row and the J column element of A is the J row and I column of the element of matrix B. So note that B should be an M by M matrix. So the transpose of A is denoted by A, then we have T on the superscript. Example, find the transpose of this matrix A. So we have, this is a 3 by 4 matrix, 25, 20, 3, 2, then 5, 10, 15, 20, then 6, 16, 7, and 27. So the transpose of this matrix, so this is, so your row will become column. So that is 25, 23, and 2. The same as 5, 10, 15, 20. Then we have 5, 10, 15, 20 in column. Then the 6, 16, 7, 27 will become 6, 16, 7, and 27. So the transpose of the row is the column vector. So the row vector or the transpose of the row vector is a column vector. And the transpose of the column vector is the row vector. So vice versa. So this is some other property of transpose matrix. So we have uh, the transpose of a certain matrix is equal to its original matrix. Also, we have when we add first A and B matrix and we are going to transpose the resulting matrix, that is the same as when we first transpose A, then add to the transpose of B. So that is the same. Then we have, let's say, C common factor, C or the multiply a common factor multiplying by or the matrix multiplied by a common factor, then we have to transpose it is the same as when we first transpose then multiply by a common factor. So that is the transpose of the matrix. Next, what is a symmetric matrix? So a square matrix A with real elements where Aij is equals to Aji for I is equals to 1 to up to n and j equals 1 to up to n. So that is called a symmetric matrix. Okay, so this is an example of the symmetric matrix where your Aij is equals to Aji. So let's say this is A12 is the same as A21. Same as A13 and A31. So that is a symmetric matrix. So what is the difference between the skew symmetric and the symmetric? So when you say skew symmetric, that is the negative of the matrix A is equals to the negative of its transpose. Example is here. So we have 1, then negative 1, 2, negative 2, then negative 5, and 5. So that is the skew symmetric. And we have also the diagonal elements for this skew symmetrics have to be 0 or the elements or entry in diagonal in the main diagonal of the matrix are zeros. Okay. Next is what is the trace of the matrix. So the trace is just the sum of the diagonal entries of the given matrix. So that is trace of A is just the summation of its entry or diagonal entries of the given matrix. So let's say we have example. So find the trace of this matrix A. So we have the sum of its diagonals. So the diagonals entries are 15, -4, and 6. So meaning the trace of this matrix is 17. So we have 15 minus 4 plus 6. That is the trace. Next, this is an example. So we have the sales of the tires, so given a row and quarter columns for blowout truss store location A. So ito yung kanyang given or representation of sale of three different tires. So we have the Firestone, Michigan, and copper tires. Then the column represent its quarter. So the sales in first, second, third, and fourth quarter. So find the total revenue of the store A if the prices vary per quarter. So the main objective here is to find the total revenue. And we all know that this given B, so this is the prices of the tires varies per quarter. So meaning they are different in each quarter. So we have to multiply each uh, term. So let's say this first quarter by first quarter, then the same is second quarter is the second quarter. So that is a normal computation in solving the total revenue. But if we are going to use the transpose and the trace matrix, so first is, so since if we are going to use the multiplication, or we have to multiply A times B, so since uh, this is the price per tire, then this is the total sale. So you have to multiply it so that you are going to make it the sales of that tire in that quarter. So since this is a 3 by 4, so we cannot multiply it in term let's say A and B because they are the same I mean the same size. So we're going to transpose it so that uh, the number of columns of this A will be equal to the number of rows of B. So if we transpose this B, so that is 4 by 3. And for that, we are ready to multiply A times the transpose of B. So this is the solution. So we have first to transpose B. So it will make a C, or let the transpose of B is equals to Z. So then we are going to multiply A times C. Then the resulting is D. So, so if we're going to get the total sale, so since um, multiplication is just multiplying or sum of the product of its its term. So let's say 25 times 33.25 plus 20 times 30. So the first column and first row will be the total sales of the tire stone. So next naman is second row times second column. So that is the total sales of the second tire. So which is the Michigan. While the copper tire, so we have to multiply the third third rows by the third column. So that is in D33. So then to sum up or to get the total sales, so we have to multiply its diagonal using trace of matrix. So we have 1597 for the total sales of Firestone plus 2152, which is the total sale of Michigan, then 1311, that is the total sales of copper. So we are going to use the trace. Okay, so this is since the diagonal elements give the sales of its brand. So the total sale is $5,060, which is the trace. Next is find the determinant of the matrix. The first is the determinant of a square matrix is a single unique real number corresponding to a matrix. So for a matrix A, determinant is denoted by it's like A, then we have absolute value or double bar, or the that of A, determinant of A. So do not use this bracket and or braces and the double bar interchangeably. Then for 2 by 2 matrix, so we just use the basket weave method. We have A11 times A22 minus A21 times A12. So this is a basket weave method, the same as in 3 by 3. So next is, let's proceed to the determinant by using the minor cofactor. So let A be an n by n matrix. So this is a square matrix. The minor of the entry Aij is denoted by Mij, which is the minor, or that is defined as the determinant of n minus 1 by n minus 1 submatrix, or that is the minor, where the submatrix is obtained by deleting the I row and the j column of the matrix. So we have to, let's say, example. So we have 3 by 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's say this, your Aij is your first row, first column. So that is A11. So after deleting your first row and first column, so the determinant of the resulting or the resulting submatrix 5, 6, 8, 9, that is your minor, or this is your minor 1, 1. Next, so the determinant is just the summation of the negative 1 I plus j times aij times mij, or the minor, for I equals 1, 2, 3, n. Or if we are going to use the column, so uh the, this is for row. So for the uh row 1 2 2 1 2 1 3 1 4 or 1 3 1 4 if 4 by 4. Next, for this determinant of A, that is the same summation negative of raised to I plus j aij mij, for j is equals to 1 2 3 to the n, up to n. Okay, so next is coupled with the determinant A is equals to A11 for a 1 by 1 matrix A, we can always reduce the determinant of the matrix to determinant of 1 by 1 matrices. So the number negative 1 raised to I plus j times mij, or minor of ij, is called the cofactor of aij and is denoted by Cij. So the formula of using this cofactor, so we have the summation of Aij, Cij for any I, 1, 2, 3, 4, and so on up to n. Then we have, this is for column, then row. Then for this determinant of Aij, Cij, for any j is equals to 1, 2, 3, and That is for column. Okay, so determinant are not generally calculated using the method as it become computationally intensive for a large matrices. For n by n matrix, it requires arithmetic operation proportional to n factorial. So let's say we have find the determinant of 25, 5, 1, 64, 8, 1, then 144, 12, 1. So using method 1, so we have first to consider uh, A AIJ then MIJ or the minor. So what is the minor? So let's say M11. So M11 is the result or the determinant or the resulting submatrix after deleting your row 1 and column 1. So that is 8, 1, 12, 1. So M11 is just the determinant of this matrix or submatrix. So this is for M11. So 8, 1, 12, 1. So that is negative 4. So for 1, 2, so we are going to use this row number 1 only. So if you use the row 2, so that is for 64, 8, and 1. Then we also possible to use the 25, 64, and 144. So for that is for column. Then we are going to use also the row. Then so we have A12. A12 is just deleting your first row and second column. So the resulting submatrix is 64, 1, 144, 1. Then the determinant of that is the minor of 1, 2. So this is negative 80. And the same is M13. So we have negative 384. So the determinant is just the summation of A11. So since we have negative 1 raised to the 2, that's positive. Negative 1 raised to the 3 is negative. Then negative 1 raised to the 4 is positive. So we have to multiply. So A11, that is the entry in your 1, 1. So here, 25, 5, and 1. So summing up, so we have negative 100 plus 400 minus 384. So the resulting determinant is negative 84. So the same as when you are using cofactor. So cofactor is just equivalent to this. So cofactor is negative. So this is for cofactor we have positive, negative, positive. So this is negative, positive, negative. Then we have positive, negative, positive. So that is for cofactor, sign of the cofactor. Okay, so this is for cofactor expansion. So next is we are going to use the column. So where your J is 1, 2, 3. So we have 1, 2, 2, 2, 2, and 3, 2. Okay, so the same pattern for the row. So we're going to get the minor 1, 2, 2, 2, and 3, 2. So this is for second column. Then using this summation, so we have negative 84. So that is the same. So replacing your negative 1 raised to the I plus j, mij, so you can get the cofactor. Okay, so that they are the same answer. So this is also what is the relationship between the determinant of AB and the determinant A and determinant of B. If A and B are square matrices of the same size, then determinant of AB is equals to the determinant of A times determinant of B. So that is possible only if they are the same size. So are there some other theorem that are important in finding? So this is some theorems in determining the determinant of square matrix. So if the row or the column is an n by n is 0, so the determinant is 0. So if A or matrix A is an n by n, so this is a square. If the row is proportional to another, then the determinant of A is 0. So meaning that you have proportional, let's say 1, 2, 3, then 2, 4, 6. So that is proportional. Okay. Next is when the column or row is multiplied by k, so the resulting matrix, k is then determinant of B is k times determinant of A. So we have constant k. What is the determinant of this? So we have, since we have a column of 0, so the determinant is 0. Same as we have, okay, so 1 and 4. 1 and 4 column, so they are proportional. So since they are proportional, so we have 0 matrix. 0 determinant. So if the determinant of A is negative 84, then what is the determinant of this? Okay, so we just, ayan, so this is 2.1 times in the second column. So we have to get the proportionality constant for this second column. So we have 2.1. So the determinant of the result or of the B is just 2.1 times the determinant of A. Okay, so this is the same. So 2.56 times the first row. Okay, so that's all for unary operation.